Full fine-tuning of an LLM takes a lot of courage. It's expensive, memory hungry, and very easy to get wrong. Parameter-efficient fine-tuning, or PEFT, fixes all three by tuning only a tiny slice of the weights. Let's see how. So I would like to set the stage so we can appreciate PEFT a little bit more. Here is our pre-trained LLM. Let's say we have a 500 billion parameter model that has been trained on 10 trillion of samples. Pretty standard setups for today's LLMs. It's already learned on enormous amount of general useful stuff. Instead of building a specialized model from scratch, we can take this massive foundation and customize it for almost any task we want. This is the core idea of transfer learning, building on what a model already knows and just teaching it the fine details of our very specific task. And the thing that matters most is how much task data do we have compared to the original training set. Look at the scale here. If you have 100 billion of samples, it feels like a lot, but it's just 1% of the pre-training data. A billion is 0.01%. A million? Basically a rounding error next to 10 trillion. Here's the classic rule of transfer learning. How much you fine-tune should match how much data you have. A little data change very little, or you will overfit and mess with what the model already knows. Lots of data, let's say at least 5 to 10%, okay, now you can afford to change the model a little bit. To see why LLMs are tricky to fine-tune, let's compare them with traditional, let's say, computer vision models like deep CNNs. Their feature builds up layer by layer. Edges, then textures, then object parts. These are just feature extraction layers. And the task-specific part is just the classification head that sits right on the top. So with a small data, we can freeze everything and just fine-tune the head. But here's the catch, and it's the whole reason why we need something new. A transformer isn't like that. There is no little head at the top doing the task-specific work. The stuff we want to change in an LLM, like the style, the format, how it behaves in a new domain, is spread across every layer top to bottom. So we can't just train the head, and just unfreezing the top transformer block doesn't save us either. One block is still 100 millions of parameters, and we would be adapting in the wrong place anyway. We need a completely different approach. Otherwise, forget about fine-tuning LLMs. LoRA stands for low-rank adaptation, and it's exactly the out-of-the-box solution we needed. And it changes the question completely. Instead of asking which layers do we fine-tune or train, LoRA says don't touch the original weights at all. Here's the idea. We freeze the big weight matrix W entirely. That pink block never changes. Then alongside it, we add two tiny matrices, A and B. During the training or fine-tuning, only those two little adapters actually learn. Because they are low rank, that skinny R dimension in the middle, they work with a tiny percentage of the parameters of a full model. You might be thinking, does shrinking that middle dimension really make that big of a difference here? Let's look at the numbers. Imagine a standard layer with a weight matrix of 4096 by 4096. Fine-tuning that matrix means updating nearly 16.6 million parameters. With LoRA using a rank of 8, we split that into two matrices. That brings us into 65K. That's over a 250 times reduction for a single layer. And that's where the massive memory and compute saving comes from. But it's not just that. Here is the more elegant part. At inference, you can just mathematically merge the adapters back into the original weights, W plus B times A. That means zero added latency. The final model runs exactly as fast as the original, but now it does your task. You get the customization of fine-tuning at a tiny fraction of the trainable parameters. Okay, so let's talk about some variants of LoRa now. LoRa was a massive win. It allows us fine-tune a huge transformer effectively while updating just 1% of its parameters. So training goes from needing a cluster of GPUs to something far more feasible. But there is still a catch. You still have to load the entire base model into your GPU memory. That frozen W block might not be training, but it's sitting there, taking up massive VRAM space. And by default, those bit weights are stored in 16-bit precision. That's 2 full bytes per parameter. So here's the question QLoRA asks. What if we squish that frozen base model down to just 4 bits per parameter? So it's still D by D, but it quantizes the frozen base weights down to 4 bits, cutting the base memory footprint by nearly 75% while keeping the small LoRa adapters in 16-bit, so quality doesn't drop. The base model becomes dramatically lighter, quality stays intact, and suddenly a giant LLM that used to need expensive enterprise hardware can fine-tune on a single consumer GPU. There's so many other variants of LoRa. Let me bring one more, and that is called rsLoRA. So far it's been pick a small r and you're good. But here's the natural instinct. If a little rank helps, wouldn't a larger one help even more? Bump R to 64 or 128 for a richer adapter with more capacity. In plain LoRa, that often does not pay off. You raise the rank and performance just flattens. People long assume that high rank simply isn't useful. To see what that actually happens, one detail I skipped earlier is important. LoRa doesn't just add BNA raw. It scales it by alpha over R. Think of alpha as a fixed volume knob. And divided by R is just a normalizing act. As the adapter gets bigger, you divide by more to keep its output from blowing up. So you can't change R without retuning everything else. rsLoRA said this normalizer is just wrong. Here's why. As you increase R, the product BA naturally grows in magnitude. You are summing up more pieces, so the output gets bigger on its own. But that growth isn't as fast as R. It's more like a square root of R. So when you divide by the full R, you're overcorrecting. At high rank, the adapter gets so damped, it barely contributes. The fix is extremely small and embarrassingly small. Divide by root square of R instead of R. Now the update stays at the right size for every rank, and higher ranks started to actually pay off with rsLoRA. Let's see one more important variant together, and that is called LoRA-FA. LoRa already brings us down to 2 tiny matrices, A and B. LoRA-FA asks, do we even need to train both of them? And the answer, surprisingly, is no. Here's the move. Freeze A at its random starting values and only train B. A just takes the white input, say if the original dimension is 4096, it compresses it down to R numbers. It turns out you don't really need a train matrix to summarize an input. Even a fixed random blend captures enough of the raw signal. All the real learning can still happen in B, which figures out how to turn that summary into the right task update. To help understand this better, picture shining light on a 3D object and reading its shadow. Even a random angle or most of the random angles are still showing us most of its shape. So LoRa-FA have cut the trainable parameters by half. And you can save the memory that training A would have cost too. You're now giving up a little expressiveness, since B is now working from a fixed random subspace rather than a learned one, but in practice the accuracy barely moves, so it doesn't matter much. Before we wrap up, let's also talk about why memory matters so much here, because this is really the whole story. We will use an example to make sense of the numbers here, and that example would be Mistral 7B model, or more specifically 7.3B. When you just want to run a model and take inference, it's cheap. The reason is that you load the weights only once, and you need about 2 bytes per parameter. So Mistral 7.3B is roughly 15 gigabyte of memory. Totally doable. But the moment you want to fine-tune it, things blow up. Now, you don't just need the weights, you also need the gradients, the optimizer states. Atom alone adds a whopping 8 bytes per parameter. Add it all up, weights, gradients, optimizer, and you're at about 12 bytes per parameter, or roughly 88 gigabyte of memory in total to be able to handle fine-tuning this model. That's more than a single A100, one of the most powerful GPUs out there. So you can see why full fine-tuning is off the table for most people, even for Mistral 7B. This is where our PEFT strategies come in. Let's see what happens with LoRa. With LoRa, we freeze the base model and only train those tiny adapters. So we drop all those gradients and optimizer states. That brings us back down to around 15 gigabyte of VRAM. And now it fits on a T4, which is available for free on Google Colab. Let's see QLoRA. So QLoRA goes one step further, right? On the top of LoRa, it compresses those frozen weights to 4 bits. Now the whole thing fits in a 4 to 5 gigabyte VRAM memory, meaning you can now fine-tune on a regular GPU on your personal laptop or even a free notebook. So we went from needing a data center to needing a standard laptop GPU. That's what made fine-tuning accessible to everyone.